Do the general case? Yeah, I can do the general case. A while back, I wrote a video about how you would prove if one sequence converged to 5 and another sequence converged to 7. If you divided them term by term, then that ratio would converge to 5/7. There were some interesting numbers in the proof, but it was fairly explicit, and I actually like using explicit numbers just to give the idea of what's going on. I'll get out of the way so you can kind of read the proof if you're interested, but we're going to ask what happens if instead of the denominator going to some number like 7, it just goes to some non-zero number b. Now, strictly speaking, we need to make sure that the denominator is never 0 or else that quotient sequence wouldn't be defined. But now we're going to see how the proof is going to change. Not surprisingly, we start by just find replace. Anytime we saw a 7, we're going to replace it with a b. And like lots of things go through unchanged. The algebra is mostly the same. And actually here, once we combine and do a little bit of factoring, we notice that the numerator is 5 plus absolute value of b times epsilon. And the denominator, instead of 7bn, is just b times bn. Now, because we know that our sequence an and bn both converge, we can put any number we want here. Now, we chose our arbitrary number epsilon here, but if we change it just a little bit, for instance, what if I were to multiply by the absolute value of b and then divide by this number here? It looks really gross when you put it all together. But then when you get to this step here, once we use the fact about those differences there, it simplifies beautifully to just epsilon over the absolute value of bn. But that was kind of the easy part, actually. So just modifying epsilon, something we may need to do all the time. But this actually requires a little bit more care. So what we did earlier was we just kind of picked a random number, 0.3. And when this limit was 7, that didn't lead to any problems. But here I'm going to show you what can go wrong. For instance, what if the limit was 0.1 and we did our 0.3? Well, it would be true. We could kind of use the facts that we know to conclude that bn has to be between 0.4 and negative 0.2. The problem is we need a bound on 1 over the absolute value of bn. And bn, for all we know, could be like 0.0000001. And then when we do 1 over it, that would be like a million or a billion. It could be arbitrarily large. So this data here is not enough for us to conclusively give an upper bound for this fraction here. Now remember, when this number was 7, it worked fine because I think we had 6.7 and then 7.3, and there wasn't this dividing by 0 risk possible. So for any specific number, you can just kind of see if 0.3 is small enough. Maybe you'd have to pick 0.03, but we just have a number b. So what are we going to do? Well, if we just move over by the absolute value of b over 2, we're never going to get close to 0. You can pause the video and check that these will either be both negative or both positive numbers. So now we have to think about what's going on here. Well, the smallest that this thing, bn, could be an absolute value, we want to see whichever one of these two numbers in absolute value is closest to 0, because we're going to do 1 over it. And so we look at those absolute values, we take the smallest of the two, and 1 over that is going to be an upper bound for 1 over bn. Phew, that was a lot. But now down here, we're just going to get epsilon over m, and now we're really great, because now m is some number, it's some non-zero number. And if we can show that the thing we wanted was less than epsilon times a constant, we're going to be able to show that it's less than epsilon. And for those of you who are purists that want to see how we get exactly epsilon, well, we can modify what we did up here so that we introduce that factor of m up here so that down below, we're going to get m times epsilon and everything cancels perfectly. And if you notice, doing that's a little awkward because we haven't defined m yet. And so we should probably do this part first. So I hope there aren't any typos in what I wrote in this proof, but this is the basic idea of how you would change that from a 7 to a general case.